Let's tackle a heat pump problem. Heat pumps sometimes get neglected in this course because they operate in the same manner as refrigeration cycles, but of course they're trying to accomplish two different engineering goals. Refrigerators are designed to keep the cold reservoir cold, heat pumps are designed to keep the hot reservoir hot. And in some cases you live in the hot reservoir, so when a heat pump is attached to your home in order to heat it, you're actually living in the reservoir. We'll use that detail in this problem. We're given that a heat pump operates between two reservoirs, one at 30 degrees C, that's your house, the other at 14 degrees C. We'll see what that is. So, you get 35 kilowatts of heat power to the house for every 28 kilowatts of heat power from the ground. We're just told that about this particular heat pump. The schematic picture that you should have in mind is this. So you're drawing up energy from the cold reservoir, and the cold reservoir can be just a big hole in the ground or maybe a well. That's where you're getting your heat into the system, though. You also have to input work into the system, right? So that explains the discrepancy between 35 kilowatts and 28 kilowatts. The remainder there is made up by the work going into the system, probably in the form of electricity. All of that energy comes out in the form of heat energy into the hot reservoir. And remember, the hot reservoir is where you live. Okay, so the temperature of the hot reservoir is 30 degrees C. Temperature of the cold reservoir is 14 degrees C. Now, we don't know the values of Q. But we do know the values of Q dot, so we're told the powers. We know that Q dot H is 35 kilowatts. We're also told that Q dot C is 28 kilowatts. Furthermore, for any heat pump, we know that its coefficient of performance, gamma, is given by the ratio of Q sub H to W cycle. And the second law also tells us that the maximum value of gamma that you can ever achieve is the temperature of the hot reservoir divided by the difference between the two temperatures for a two-reservoir system. Now remember, gamma is not subject to the same restrictions that the efficiency of a power cycle is. Gamma can exceed 1, no problem, and in fact the maximum value of gamma that you can get is given by that expression down there. It depends on the temperatures involved. So what we're going to do in this problem is compute the actual coefficient of performance for this heat pump that we've built, and then we're going to compare that to the maximum coefficient of performance you could ever get for a heat pump working between those two temperatures for those two reservoirs. Okay. So let's start by computing the actual heat pump performance. Well, gamma just equals Q sub H over W cycle. We can rewrite W cycle in terms of Q sub H and Q sub C. Remember, it's just the difference between those two because energy is conserved. Now, I'm going to pull a trick here and say that, this thing is operating as a cycle, but it should be in a steady state, at least if you take a long enough time average. So I'm going to replace all of those undotted values with dotted values. How can I get away with that? Well, really, all I've done is basically just gone through and divided Q sub H by delta T and Q sub C by delta T. If I do that to the numerator and denominator, consider the same time interval, that should be fine. Well, now we know these values, right? We know QH dot and we know QC dot, so we can plug in those values. And we see that indeed we're going to get a gamma value that does exceed 1. In fact, gamma for this heat pump is equal to 5. So that's our coefficient of performance for the actual heat pump that we're using, based on the amount of power that goes into the house and the amount of power that comes up out of the ground. Okay, we'll record that value over here on the left so we remember. Now, what's the best we ever could have done with any heat pump going between these two reservoirs? Well, that's just going to be the value of gamma max, right? And that depends upon the temperatures of the reservoirs. So gamma max is TH divided by the difference in temperatures between the two reservoirs. Here you do have to be careful. You do not want to take this ratio in Celsius. You want to take it in Kelvin. So we have to convert to Kelvin. That's not so bad. We're going to get a ratio of 303 to 16. Okay, this is going to be a lot bigger than 5. The ratio comes out to be about 19. So we built a heat pump that we thought was actually doing pretty well with a coefficient of performance of 5. If we had somehow been able to build one without any internal irreversibilities or anything like that, maybe we could have achieved the ideal maximum, which is 19, considerably better than 5. So these are the two numbers that we compare. Engineers strive for gamma max, but of course they never quite hit it.